Last time we derived this Riemann functional equation written in this form. Now we are going to study what's going to happen near the point s equal to 0. We are going to have problems if you just plug in into this equation this value here, because you will have zeta of approximately 1. So zeta of 1 will go to infinity. So this is a divergent value. However, if you consider the product between the sign of pi s over 2 zeta of 1 minus s, well, of course, the sign of pi times s over 2 as s goes to 0 can be approximated by the argument itself. So it's approximately pi s divided by 2 zeta of 1 minus s. It is possible to show that this value here is not divergent anymore. And it is exactly what I want to show you here in the next few steps, and I want to derive some properties of the Riemann Zeta function for some specific values, and in particular of the derivative of the Riemann Zeta function. As s goes to 0, it is possible to show that zeta of 1 minus s behaves in the following way, as minus 1 over s plus gamma, which is the Euler-Mascheroni constant, plus something of the order of s. So as s goes to 0, this term becomes negligible, and of course this is the part that prevails, and in particular this one here. This also means, of course, that zeta of z, as z goes to 1, behaves like this, 1 over z minus 1 plus gamma plus something of the order of z minus 1. So this is as z goes to 1, and this one holds for s going to 0. Now let's show that indeed we have such relationships. If we start from the definition of the Riemann zeta function for the real part of s greater than 1, we know that we have a summation of this kind. We have a summation over the integers from 1 to infinity. Now let me put here capital N, and you have to imagine that this n here will go to infinity. Here you have 1 over n to the s. So this summation holds if the real part of s is greater than 1. We know that we can consider an analytic continuation of this function, in particular this summation here can be extended also for real parts of s which are less than or equal to 1. Anyway, if we start from here and we just do a little bit of a manipulation, very simple algebra here, so I'm going to consider the following. This is equal to the same summation, of course. Then we are going to subtract the integral from 1 to capital N of 1 over x to the s dx. Of course, I also have to sum the same integral. Integral from 1 to capital N 1 over x to the power s dx. Now, as s goes to 1 plus, remember that here we should consider 1 plus because this definition here for the Riemann zeta function is correct if we assume that the real part of s is greater than 1. So we can take some kind of limit as s goes to 1 plus, and of course we also have to assume that n goes to infinity, as I said. Now this difference inside these parentheses here will tend to the Euler-Mascheroni constant. This is exactly the definition for the Euler-Mascheroni constant. I will say more about the Euler-Mascheroni constant in the next few videos, but this is actually the definition for the Euler-Mascheroni constant. Now, of course, here we have gamma. So now I'm assuming, of course, that we are reasoning in these limits as n goes to infinity and as s goes to 1 plus. Then here, if we calculate this integral, we have the following. So we have x to the power minus s plus 1 divided by 1 minus s, and we have to evaluate it between 1 and capital N. Now, as n goes to infinity, you have to notice the fact that also we have s which tends to 1 plus. So this exponent here will be slightly negative. So we have infinity raised to something slightly negative, or actually instead of infinity, just think of a very large number here, which is raised to an exponent which is negative. So we will get something which will become very, very small, right? Of course, this is just intuitive because it's not mathematically rigorous, but you have to think that this is the case. And of course, then you have to evaluate it at x equal to 1. So you have gamma minus 1 divided by 1 minus s. And this is, of course, an approximation. This is an approximation of the Riemann Zeta function evaluated at s. This approximation holds near the point s equal to 1. Near s equal to 1. And from here you can see that zeta of 1 minus s is approximately minus 1 over s plus gamma from here. So you just simply redefine this 1 minus s as the new s, right? And therefore you can write something like this. So you can see that the limit as s goes to 0 of s times zeta of 1 minus s is equal to minus 1, and also the limit as s goes to 0 of the derivative of s times zeta of 1 minus s. So I'm indicating the derivative with this prime. It is the derivative with respect to s, and of course this is equal to gamma, the Euler-Mascheroni constant. And you can see it from here, because if you multiply s and then you have zeta 1 minus s, this is approximately minus 1 plus gamma times s, and then you have higher order terms. So when you let s go to 0 here, because in this case you have to think that this holds near the point s equal to 0, right? So near s equal to 0 you get this approximation, and of course you get these two limits, which are something that we are going to use. Now, if we start from the Riemann functional equation, this equation here, we can rewrite it near the point s equal to 0. So near the point s equal to 0, zeta of s is approximately, so let's rewrite it as 2 pi to the power s divided by pi. Then instead of the sign, we write the argument, so pi over 2 s. So here we would have the sign of pi over 2s, but near s equal to 0 we can replace the sign with its argument. Then we have zeta of 1 minus s times gamma of 1 minus s. So we can consider, let me just cancel this part because I don't really need it. So I'm going to cancel this. I can also cancel the pi from here and here, and I can put these 2 here. And let me consider s times zeta of 1 minus s as just one single entity. You can see that when s approaches 0, zeta of 0 is equal to minus 1 half. You can see that because gamma of 1 will be just 1, and then this quantity, when you let s go to 0, you can see it there, it will give minus 1. Of course, this 2 pi to the s will go to 1 because we have 2 pi to the 0, and then you are left with these 2 in the denominator, therefore zeta of 0 will be minus 1 half. Now I want to calculate the derivative near the point s equal to 0. So we want to evaluate 0 prime of 0, but in order to do that, let's calculate the derivative from this expression. So this derivative will be approximately equal to 2 pi to the s. Then we have the natural logarithm of 2 pi when you take the derivative of this first term divided by 2, and then of course you have s times zeta of 1 minus s, gamma of 1 minus s, and of course when we let s go to 0 we will have to set minus 1 in place of this expression. This will give us 1, and this will give us 1, of course. But remember that you also have other terms to consider, so we have to take the derivative of this one as well. And then we also have to take the derivative of this gamma function. So we have 2 pi to the power s divided by 2. And then what do we have? We have the derivative of s times 0 of 1 minus s times gamma of 1 minus s plus 2 pi to the s divided by 2 s times 0 of 1 minus s. Then here we have to evaluate the derivative of gamma of 1 minus s with respect to s, and then we have to set s equal to 0. So when we set s equal to 0, here we will get the derivative of the gamma function evaluated at 1, like this. So here I have already set s equal to 0 in this expression, because at the end of the day, that's what we want to do. When s equal to 0, of course, 2 pi to the s will give me 1. Then when we evaluate this derivative here, at s equal to 0, we will get gamma, so the other Mascheroni constant. Gamma of 1 minus s, when s goes to 0, will be 1. This will be 1. S times 0 of 1 minus s will give me minus 1, because it is this limit here. And finally, we have to evaluate gamma prime of 1. Now, I will say more about the derivative of the gamma function at 1 in the next few videos, because I want to show you exactly why it is equal to an expression that I will write down here. In particular, let's start from gamma of 1 plus epsilon, where epsilon is small. This is equal to epsilon times gamma of epsilon according to a simple property of the gamma function. Now, gamma of epsilon, it is possible to show that when epsilon goes to 0, it is approximately equal to 1 over epsilon, and then we have minus gamma, which is exactly the Euler-Mascheroni constant. So this expression clearly diverges as epsilon goes to 0 because we have 1 over epsilon. But you can see that here, if I consider epsilon times gamma of epsilon, this will be approximately 1 minus epsilon gamma. And now if you take the derivative, of course we have gamma prime of 1 plus epsilon, where epsilon is small, which is equal to minus gamma. So this is approximately equal, but when you let epsilon go to 0, you will get an equality. So gamma prime of 1 is equal to minus the Euler-Mascheroni constant. The Euler-Mascheroni constant, as you can see, it is something that often appears when we deal with the gamma function and the Riemann Zeta function. In the next few videos, I want to show you why gamma of epsilon can be approximated in this way. But here we will use this fact, so minus gamma prime of 1 will be equal to gamma, the Euler-Mascheroni constant. Therefore, zeta prime of 0 will be equal to, and it is exactly equal to what we see there, so we have minus natural log of 2 pi divided by 2. Then we also have plus gamma halves from here, but we also have minus gamma over 2 from the last term. And therefore, these two will cancel. And we are left with minus natural log of 2 pi divided by 2, which is an expression for the derivative of the Riemann Zeta function at 0. Now, if we started from the Riemann Zeta function written as a summation, and we know that the summation strictly holds for the real part of S greater than 1. But now we know that in general the Riemann Zeta function can be extended by means of the so-called analytic continuation. So this infinite series will get some corrections to cancel out the infinities. But let's assume that we can use this definition here also for values of S that do not comply with this condition here. So let's calculate the derivative with respect to S of zeta of S. So just define it as zeta prime of S. This is the derivative with respect to S of this infinite summation from 1 to infinity. We can rewrite 1 over n to the s as e to the minus s natural log of n. Now, we assume that we can change the order between this summation and this derivative, so we can rewrite it as summation over n from 1 to infinity natural log of n divided by n to the s, and we also have to put a minus sign, so we also get this minus sign minus natural log of n divided by n to the s. Well, this clearly diverges as we let s go to 0 because we have a summation of this logarithm from 1 to infinity, and that will be a divergent sum. But what the derivative of the Riemann Zeta function tells us, and in particular I'm referring to this here, so when we let s go to 0, well, that tells us that we can in some way regulate a series of this kind, summation over the integer from 1 to infinity, natural log of n, we can, in some sense, associate this infinite summation with the natural logarithm of 2 pi divided by 2, just like in here. So you can see that there is some kind of association that can be made between this series, which is divergent. Remember, this is actually equal to infinity if you want. This goes to infinity. But it can be regulated in such a way that it can be associated to this value, to this real value here, just like, for example, zeta of 0 is equal to minus 1/2, and we can make a similar association between the summation over n from 1 to infinity of 1, we can associate it to the value minus 1/2. Such divergent expressions appear in physics, which apparently doesn't make sense, but it can be actually done thanks to the properties of the Riemann zeta function.